Hey everyone, and welcome. On behalf of Forge College, I am absolutely thrilled to be your guide for today's explainer, defining and initializing structs. Now, if you're watching this, congratulations. It means you've successfully survived our previous lesson, Introduction to Structs and Arrays, which is a massive step in our Solidity from Zero journey. You've got the core concepts down, right? So it's time to put on our hard hats. Today, we're taking that inventor's blueprint we talked about and learning how to actually build with it. We're moving out of the conceptual realm and diving straight into practical, real-world patterns in Solidity. Let's get right to it.
Here's our master schematic for the day. We'll be covering blueprint basics, persistent storage, temporary memory, default values, storage mutations, and wrapping it all up with some key takeaways.
Starting right off with Section 1, Blueprint Basics and Recap.
So, just as a quick refresher, a struct in Solidity is basically a custom composite data type. Think of it as a way to bundle multiple named fields together under one single, neat identifier. Instead of having a user's ID, their name, their wallet address, and, say, their active status scattered all over your smart contract, kind of like loose tools rolling around on a workbench, a struct packages them all up perfectly. It just keeps our code incredibly organized and logically sound.
Moving on to Section 2, Building in Persistent Storage.
Now, understanding storage is absolutely vital in Web3. Storage is the permanent, persistent state of the blockchain. You can think of it like drafting your master blueprint in permanent, indelible ink right onto the main ledger. When we construct a person struct and push it directly into our dynamic people array, we are writing directly to storage. That push operation creates a brand new permanent slot on the blockchain. It's super powerful, but because it's permanent, it costs gas. And gas is money. All right, on to Section 3, temporary copies in memory. On the flip side, we have memory. Think of memory as a temporary, transient data area that only exists while a function is actually running. It's like sketching out your blueprint with an erasable pencil instead of that permanent ink we just talked about. When we construct a person struct and explicitly use the memory keyword, we're just creating a temporary snapshot. We can fill in the fields, read them, maybe hand that snapshot back to whoever called the function, and the moment that function finishes, poof, that pencil sketch is thrown in the trash. It doesn't alter the permanent state at all, which makes it incredibly cheap. Let's compare these two side by side to really solidify the difference. Over on the left, we've got storage. You build the literal struct and push it straight into the array. That writes directly to the blockchain, it's persistent, and yes, for sure, it's expensive gas-wise. Now on the right, we have memory. You declare a variable like person memory p, fill out the fields, and hand it off. It's temporary, transient, and cheap. Knowing exactly when to pull out your permanent marker versus your erasable pencil is quite literally one of the most vital skills you can develop as a Solidity engineer. Now, let me throw a quick question your way, just to build a little tension here. What do you think actually happens if we declare a memory struct, say person memory p, but we totally forget to fill out any of the fields before we return it? What does the Solidity compiler do with a completely blank blueprint? Does it crash? Does the whole thing panic? Let's find out. Which brings us to Section 4, the uninitialized default struct. Okay, so no, it doesn't crash. If you leave fields uninitialized, Solidity just defaults them to their type's 0 state. For a uint256, like our ID, it defaults to exactly 0. For a string, it defaults to an empty string. The wallet address, that defaults to address 0, which is effectively the burn address. And for a Boolean, like our active status, it defaults to false. So our completely blank uninitialized person is basically an entity with a 0 ID, absolutely no name, a totally voided wallet, and they are completely inactive. Kind of a sad existence, right? But honestly, knowing these exact defaults is absolutely crucial for reasoning about safety checks in your smart contracts. Let's jump right into Section 5, mutating with storage references. When you need to update a struct efficiently after it's already on the blockchain, we use a really neat 3-step process. Step 1, we grab a storage reference. We do this by declaring person storage p equals people index. Notice, we are not making a copy here. We are pointing directly at the original array element. Step 2, we mutate the specific field in place. We just type p.active equals true. And step 3, we save gas. By doing it this way, we entirely bypass the massive gas tax of copying and rewriting the whole potentially huge struct just to flip a single Boolean flag. To put it simply, modifying a storage reference updates the array entry in place. Think of a storage reference like a direct, hardwired connection straight to that original permanent ink on the blockchain.
You don't have to erase the entire page and painstakingly redraw a new one. You just reach right in, update the exact fields you need, and boom, you're done. It is incredibly gas efficient for targeted updates because it completely skips that expensive full struct ABI copy.
All right, wrapping things up today with Section 6, Key Takeaways.
Here are your 3 golden rules for struct engineering. Number 1, explicitly initialize your fields. When the data really matters, don't just rely on that blank default person. Be intentional about what you're saving. Number 2, mutate with storage references. When you're updating an existing entry in an array, use a storage reference to do it in place. Your users' gas wallets will thank you. And number 3, return memory copies. If you're just showing a snapshot of data to a caller, always build and return a memory struct so you don't accidentally scramble the permanent state. Stick to these 3 rules and your smart contracts are going to be clean, gas efficient, and rock solid.
So the big question, are you ready to tackle array access patterns and loops? Because that is exactly what our next lesson in this module is going to explore in depth. But before you jump over there, chew on this for a second. As your contracts scale up to hold thousands of these user blueprints, how much gas do you think you could waste by choosing the wrong storage location just once inside a massive loop? It adds up fast. Anyway, I want to sincerely thank you for tuning into this explainer on behalf of Forge College. To keep pushing forward on your Web3 journey and check out the rest of the Solidity from Zero track, head over to our website at forge.college. Keep building, keep experimenting, and I'll see you in the next explainer.